Are we alone in the universe? Or is there an alien out there right now wondering the same thing while sipping on a cup of extraterrestrial tea? It's not that far off if you think about it. Recent studies suggest there could be up to 40 billion habitable planets in our galaxy alone. That's more potential neighbors than grains of sand on your favorite beach. So, what if we're not the only intelligent life in the universe? Will we finally get invited to the intergalactic party? To answer these questions, we first need to grasp the sheer scale of the universe. It's easy to say billions of galaxies or billions of stars, but what does that really mean? How can we even begin to comprehend these astronomical numbers? Well, let's try to visualize it. Imagine if every grain of sand on every beach on Earth represented a star. Now imagine that for each of those grains, there's a whole other beach filled with grains representing planets. That's the kind of scale we're talking about when we discuss the universe. It's mind-blowing, isn't it? So if there are about 100 billion galaxies in the observable universe and each galaxy, on average, contains 100 billion stars, that's a 1 followed by 22 zeros worth of stars. And if each star has at least one planet, like our Sun does, that's an equally mind-boggling number of planets. Now, not all of these planets will be habitable, but even if a tiny fraction, say 1 in a billion of those planets were similar to Earth, that would still mean there are a billion Earth-like planets out there. And if just 1 in a billion of those had life, we'd still be talking about 1 million planets with life in the observable universe. So, with all these stars and planets out there, it seems more likely that we're not alone in the universe, right? But how can we turn these astronomical numbers into a guess for the number of alien civilizations? Well, there's an equation for that. Meet the Drake equation. It's like a recipe for estimating how many civilizations might be out there in the Milky Way galaxy. It was made in 1961 by astrophysicist Frank Drake. The Drake equation isn't about pinpointing an exact number, but rather sparking scientific conversation about the search for extraterrestrial intelligence, or SETI. It takes into account factors such as the rate of star formation, the fraction of those stars with planetary systems, the number of planets that could potentially support life, the fraction of planets where life actually develops, the proportion of life that evolves into intelligent beings, and the length of time such civilizations release detectable signals into space. Now let's apply some numbers to this equation. We'll start with a conservative estimate, assuming 5% of all stars host planets. Among these, let's say 20% have planets in the habitable zone. If we then consider that life develops on just 0.1% of these planets, but intelligent life emerges on 0.1% of the planets that develop life, we're left with a small fraction. Now, if we assume that 10% of these intelligent life forms develop detectable technology, we can start to see the potential for a significant number of civilizations. We end up with a staggering number. Even with these conservative estimates, we could have around 1,000 detectable civilizations in our galaxy alone. And remember, as we said earlier, there are an estimated 100 billion galaxies in the observable universe. Now, if we want to calculate these numbers across all those galaxies, we're talking about a possibility of 100 trillion detectable civilizations out there. But like any recipe, the Drake equation is only as good as its ingredients. Some critics argue that we're just guessing at the values for most of these factors, which makes the results pretty speculative. And others point out that the equation doesn't consider how long an intelligent civilization might last, which could seriously change the number of civilizations we might find. Despite these criticisms, the Drake equation gives us a framework to think about the factors that might influence the existence of intelligent life beyond Earth. Alright, so we've crunched the numbers with the Drake equation, but let's not forget, we're dealing with a universe that loves to surprise us. So let's dive into the realm of possibilities and explore life as we might not know it. For example, let's take a planet with lower gravity than Earth. Over time, life forms on this planet might evolve to be much taller than us. So a 20-foot tall alien might not be as far-fetched as it sounds. Or how about life forms that thrive in extreme conditions? On Earth, we have creatures called extremophiles that live in total darkness and bone-crushing pressure in the deep sea. Who's to say the universe isn't teeming with such hardy life forms? This brings us to the concept of the Goldilocks zone. The term comes from the children's story Goldilocks and the Three Bears, where Goldilocks prefers her porridge not too hot, not too cold, but just right. In the context of space, the Goldilocks zone refers to the habitable zone around a star where the conditions are just right, not too hot or not too cold, for liquid water to exist on the surface of a planet. Why is liquid water so important, you might ask? Well, from everything we've learned about life here on Earth, water seems to be a must-have for life to exist. Think of water like a universal mixer. It can mix more different things together than any other liquid we know. This mixing ability is super important because it allows all sorts of different chemicals to come together and react, which is what happens in all living things, hence the name universal solvent. The exact range of the Goldilocks zone depends on the size and temperature of the star. For a star like our Sun, Earth is right in the middle of the Goldilocks zone. If Earth were much closer to the Sun, its oceans would evaporate much farther away and the oceans would freeze. Either scenario would be inhospitable to life as we know it. But remember, the Goldilocks zone is based on life as we know here on Earth. The universe is a vast and diverse place, and it's possible that life could exist under conditions very different from those on Earth. So while the Goldilocks zone is a good starting point in the search for life, it's not the only place we should be looking for. Who knows, maybe there's a methane-breathing alien out there, sipping on a cup of liquid nitrogen. However, finding a habitable planet is one thing, finding signs of life is another. That's where biosignatures come in, signs of past or present life that might be detected on other planets, like specific patterns of chemicals or structures. For example, one biosignature could be the presence of oxygen in a planet's atmosphere. On Earth, plants produce oxygen through photosynthesis, so finding oxygen on another planet would suggest the presence of similar life forms. So while we're still waiting for that invitation to the intergalactic party, scientists are hard at work looking for these cosmic RSVPs. And who knows, maybe one day we'll be the ones sending out the cosmic party invitations. But before we get too ahead of ourselves, let's take a step back and consider the laws of physics. You see, these laws are universal. They apply here on Earth, on Mars, even in the Cartwheel galaxy 130,000 light-years away from us. Take gravity, for instance. It's the force that keeps us grounded on Earth, governs the orbits of planets around stars, and even influences the shape and structure of galaxies. It's like the universe is a giant kitchen, and the laws of physics are the recipe for life. Now, this raises the question, if the ingredients for life are so abundant, why haven't we heard from our cosmic neighbors yet? This is what's known as the Fermi paradox. Named after physicist Enrico Fermi, it's the apparent contradiction between the high probability of extraterrestrial life and the lack of contact or evidence for such civilizations. It's like throwing a party and realizing you're the only one who showed up. Awkward, right? One possible answer to Fermi's question is the concept of the Great Filter. This is a hypothetical event or stage that prevents civilizations from colonizing the universe. It's like a cosmic roadblock that could be in our past, present, or future. If it's in our past, we're lucky to have survived it. If it's in our future, well, let's just say we might want to hold off on sending those party invitations. Because if the Great Filter is ahead of us, it means we have yet to face a challenge so great that it might prevent us from becoming a spacefaring civilization. As we continue our search for extraterrestrial life, we're not just looking for our cosmic neighbors. We're also trying to understand our place in the universe and what our future might hold. But how exactly are we conducting this search? What tools and techniques are we using to reach out into the cosmos? To answer this, we have to go back to the SETI, or the Search for Extraterrestrial Intelligence. It is one of the most well-known projects in this field. SETI uses large radio and optical telescopes to listen for signals from space that could indicate the presence of intelligent life. It's like trying to find a needle in a haystack if the haystack was several billion light-years wide. Over the years, SETI and other similar projects have had some intriguing close calls. One of the most famous is the WOW signal, detected in 1977 by the Big Eater Radio Telescope at Ohio State University. This strong radio signal was significantly stronger than the background noise. It was so exciting, it was like finding a four-leaf clover in a field of grass. Except, this clover was beaming signals from deep space and then decided to play hard to get because despite extensive efforts, we've never been able to detect the signal again, and its origin remains a mystery. More recently, astronomers have been using the Kepler Space Telescope to look for exoplanets that could harbor life. The Kepler Space Telescope does this by looking for dips in brightness that occur when an orbiting planet crosses in front of its star. In 2015, they discovered Kepler 452b, an exoplanet about 1,400 light-years away. It's in the habitable zone of its star and is roughly the same size as Earth, earning it the nickname Earth 2.0. While Kepler 452b is an exciting discovery, there have been more recent discoveries that could also be mentioned. For instance, the 7 Earth-sized planets found orbiting the star TRAPPIST-1, 3 of which are in the habitable zone. So while we might not have found definitive proof of extraterrestrial life yet, our search is far from over. Each new discovery brings us one step closer to answering the question, are we alone in the universe? And who knows? Maybe the next signal we detect, the next planet we discover, will finally bring us the answer we've been seeking. But until that day comes, we'll keep scanning the stars, because the universe is a big place and we've only just started to explore our cosmic neighborhood. As we've journeyed through the cosmos today, we've pondered the vastness of the universe, the mind-boggling number of stars and planets, and the tantalizing possibility of life beyond Earth. We've explored the Drake equation, the Fermi paradox, and the concept of the Great Filter. We delved into the search for extraterrestrial intelligence and the hunt for exoplanets. And we'd even imagined what life might look like under different conditions, from towering aliens on low-gravity planets to hardy extremophiles thriving in the most inhospitable environments. But the question remains, what would it mean for humanity if we discovered extraterrestrial life? Would it change our perspective on our place in the universe? Would it unite us as a species, knowing we're not alone in the cosmos? Or would it challenge our very conception of life itself? Let us know what you think in the comments section below, and if you enjoy this cosmic journey and want to keep exploring the mysteries of the universe with us, don't forget to like, share, and subscribe. The cosmos is vast and full of wonders, and together we'll continue to unravel them one star at a time.